Remember about MA. MA has no unit because it is a ratio of load to the effort. So it is a ratio of two similar quantities. That's why it will not have any unit. Okay. Now we start with another and a very important term, and that term is called as velocity ratio. Now what is velocity ratio? We always call it as VR, the ratio of the velocity of the effort to the velocity of load is called the velocity ratio of the machine. So what is basically a velocity ratio? It is the ratio of velocity of effort to the velocity of load. Is called the velocity ratio of the machine. Okay. Now if you look at the formula of it, the velocity ratio comes out to be the velocity of effort, which we write as V subscript E, to velocity of load, which we write as V subscript L. So what is velocity ratio? It is a ratio of velocity of effort to the velocity of load. Now we need to understand what is the meaning of the word velocity of effort and velocity of load. So we understand it by a very simple term. Let dl and dE are the distance moved in the same time by the load and the effort respectively. Means what? When the machine works, when the machine is in operation, you will find that the load and the effort, they move. Obviously the load will also move, and there will be the movement in the effort as well. So there will be some displacement of load, and there will be some displacement of effort, and this displacement will obviously going to take place in the same time t by the load and the effort. Okay, so the velocity of load. Now how we'll find out the velocity of load? We know velocity is nothing but displacement upon time. So the velocity of load will be the displacement of load upon displacement of load upon time. And what will the velocity of effort? It will be the displacement of effort upon time. So velocity ratio will be velocity of effort upon velocity of load. But velocity of effort is the displacement of effort upon time divided by the displacement of load upon time. Now if you will find dE by T divided by dL by T, which will come out to be the displacement of load upon displacement of time. Okay, so obviously we can conclude that my velocity ratio can also be called as the displacement of effort upon displacement of time. So we can define velocity ratio as the displacement of effort to the displacement of load. Again, now we will figure out what happens and what is the use of velocity ratio. First of all, velocity ratio is defined as the ratio of velocity of effort to the velocity of load. But you can simplify it, and we can conclude that it is also the displacement of effort to the displacement of load. But again, the question comes, sir, what velocity ratio helps us to find out? So again, velocity ratio helps us to find out whether my machine is a force multiplier, or is it a gain in speed, or is it only used to change the direction of effort. So we use velocity ratio to figure out what our machine actually is. Okay, is it a force multiplier, is it a gain in speed, or is it only used to change the direction of effort? Now to explain this velocity ratio, just remember the definition of it. Velocity ratio is a ratio of the displacement of effort to the displacement of load. Just remember this term. Now I will stop sharing this one, and I will share another screen with you, which will help us to find out this very well. So this is our screen. Now find out let's find out easily what is velocity ratio. Now here I am keeping the load of 20 kg. Okay, so I keep it here. I keep it here. I marks it. Okay, so this is the load of 20 kg. I kept it here. So this is my load. Okay, so this is my load, and I want to lift it by 5 kg. Okay, so you all know we can do it by placing it at 5 by 8. Okay, we can easily lift it. Okay, so let me label it first, that what is all about. Okay, so we start with the first. Now this is, let me write it here, load. Load is equal to 200 Newton. Okay, 200 Newton is the load. And how much is my effort? So effort is 5 kg, means 50 Newton. So this is my load and that's my effort. Okay, so be very clear what's my load and what's my effort. So my load is 200 Newton and my effort is 50 Newton, because we assume 1 kg is equal to 10 Newton. Now we have to figure out the displacement of load and displacement of effort. Okay, so how I'm going to do it? So what I'm going to do, I'm just going to take a point. I just take a point like this here. This, I'm just highlighting this point. So this is my, okay. What is this? Oh, let me make it with red color. Clear it. Let me make this point, this end where the beginning of, okay, so here at the base I have made the point and mark the point, and obviously I'm going to place the effort here. So this is another point. These are 2 points. Okay, the initial point, this is the initial point of load, and this is the initial point of, at 2 I have marked the initial point of load, and at 8 I have marked the initial point of effort. Now we want to find out how much is the displacement of load and displacement of effort. So I place 5 kg object at 8 and see what happens. Okay, so you will find that the object has, from here, this red point, it reaches here. Okay, and here this was the red point and it reaches here. Okay, so from this now you can easily figure out this distance. This distance is my displacement of effort, and this distance from this end to this distance is my displacement of load. Exactly. So what we figure out, you will figure out, look at this. Okay, so I will just mark it here. This distance is my displacement of load, which we label as d small d n. This is displacement of load. And this point, this distance, can you see it's such a small distance? Such a small distance, this distance. Okay, so you will find it that this distance is my displacement of, sorry, this is the displacement of load. I'm so sorry. This is the displacement of load. This is the displacement of load, and that's my displacement of effort, which is d small d and capital. Okay, so understand now displacement of load and displacement of effort. This will help us to understand velocity ratio in a bigger term. See, how much is my load? My load is 200 Newton. How much is the effort? The effort is 50 Newton. And when I kept it here, I will show you again by moving it. See, I lifted it. I lifted. See, look at the displacement of load and displacement of effort. This is the initial position of effort. This is a final position of effort. So if I place it, you will find that's my displacement of effort. Okay, and here if I remove it again, look at this. This is the initial position of load, and then when I place it, you will find that's the final position of load. So that's my displacement of load. So what you find? What is your conclusion? Which is bigger here? If you give a thought to it, this line and this line, which is bigger? So we observe that my displacement of effort is greater than the displacement of load. Okay, so if I find out the velocity ratio, what I will find out, I will figure it out that velocity ratio is nothing but the displacement of effort to the displacement of load. So obviously here you can easily find out that since my displacement of effort is bigger and the displacement of load is smaller, then this answer will definitely be more than 1. And look at it, if it is more than 1, what we can conclude? My velocity ratio is coming out to be more than 1. We can easily conclude that this machine is a force multiplier. What is this machine? This machine is a force multiplier. How it is a force multiplier? Look at the load and look at the effort. My load is 200 Newton. And what is my effort? My effort is 50. So obviously, if you check it carefully, what is the MA? MA is coming out to be the ratio of load upon effort. And my answer of MA is also coming out to be more than 1. So this machine is a force multiplier. How much is the actual force required to lift the object? 200 Newton. But how much we are applying? We are applying only 50 Newton. So here you can find out that with the help of the velocity ratio as well, we can find out whether my machine is a force multiplier or a gain in speed, or it is only to change the direction of effort. Please copy this, students. Please copy this. And if you have any queries, please ask. If you have any query, please ask. I hope you are getting it better. What is velocity ratio? Velocity ratio is nothing but it is the ratio of displacement of effort to the displacement of load. And we have just seen that my load is 200 Newton and my effort is 50 Newton. And when we check the displacement of load and the displacement of effort, how much was the displacement moved and how much was the displacement in effort, we figure out that the displacement of effort was more than the displacement of load. And that's why your velocity ratio is coming out to be more than 1. And that's why if my velocity ratio is more than 1, my system is working as a force multiplier. Okay, have you copied it? And if you are having any doubt, please ask. Else type yes in the chat box so that I am pretty sure that you are getting it. Okay, okay, please, all of you, please type better because these are the new concepts. So I want you to be very much clear that are you getting it or not. If you have any doubt, please keep on asking it. Okay, very good. So what is velocity ratio? It is a ratio of displacement of effort to the displacement of load. And what it is used to? It is used to determine whether the machine is a force multiplier or a gain in speed, or it is only used to change the direction of force. So here we figure out that my load is 200 Newton and the effort required is 50. So obviously with the help of the MA, we can conclude that it's a force multiplier, but even with the help of the velocity ratio, we concluded that it's a force multiplier by looking at the displacement of load and displacement of effort. Okay. Now I will show you the second part. Okay, I'm clearing everything. Now I'm showing you the second part. Now, what I'm doing, I'm keeping an object 5 kg at 8. So what is this? Now understand, this 5 kg which I have kept at 8 is a load. How much is the load? Load is equal to 50 Newton. How much is the load? Load is 50 Newton. Now I want it to be lifted, and I'm going to lift it with the help of 200 Newton. So how much is the effort I'm going to apply? So I'm going to apply a effort of 200 Newton. Understand? On the left hand side, what I am keeping is load, and the right hand side, what I'm going to keep is always going to be the effort. So how much is the load? The load is 50 Newton. How much is the effort? 200 Newton. So I'm going to use this 220 kg mass to lift it. Okay. Now again, I am more interested in finding out the displacement of load and displacement of effort. So I have to mark the initial position of load and effort. So this is, here I am marking at the base. Here I am marking the initial position of the load. Okay, and where I have to keep it? Here at 2 I am going to place, at 2 I am going to place the effort. Here at 2 I am going to place the effort. So I mark at both the places, I have marked the points. Okay, now what I'm going to do, I'm going to lift, I'm going to place this 20 kg. This is my effort I am applying to lift it. Okay, so I place it here. Okay, and you will find it's getting lifted. Okay, now let's find out how much is the displacement of effort and the displacement of load. So here you will find this was the initial position, but chalo, from here the displacement is till here. This is the displacement. So what is this? This distance is nothing but this is my, this distance is nothing but this is my, this distance is my displacement of effort. What is this? This is the, sorry, this is the displacement of load. This is the displacement of load, which I will label as displacement of load. Okay. This is my displacement of load now, because this is the distance by which the load has moved. And let's find out how much is the distance by which the effort has moved. So we started here. Okay, you find out, see here, this is the point you can figure out. Here there is a red dot. Okay, so that's my initial position, and this is my final position. So it's, wait a minute, I will check, I will take a different color. So you will find it started from here and it is still here only. So that distance, that small distance is nothing but that's my, that distance is actually, this distance is actually the displacement of effort, which we will call as displacement of effort. Okay, so look at the displacement of load and look at the displacement of effort. Now let's find out the velocity ratio. Let's find out the velocity ratio. So we know what is velocity ratio. Velocity ratio is equal to the displacement of effort to the displacement of load. Okay. Now what you can see from this diagram, you can easily find out that my displacement of load is greater than the displacement of effort. Okay. So our velocity ratio, you will find here, the velocity ratio is the displacement of effort upon displacement of load, and displacement of effort is less and the displacement of load is more. So what you will find? You will find that this answer will come out to be less than 1. What this answer will be? If you figure out that my displacement of load is more and the displacement of effort is less, so a smaller number divided by a bigger number, and you will definitely find that the answer will come out to be less than 1, and you will figure out that this machine is working as a gain in speed. What it is working as? It is working as a gain in speed. Okay, so this helps us. Now see how it is a gain in speed. Here I am applying, here the displacement is less, here on the other end the displacement is more. Exactly, near the effort the displacement is less, but at the load the displacement is more. So definitely this machine is working as a gain in speed. So here there will be less movement, but here I will get more movement. Okay, and this will take place in the same interval of time. So my velocity ratio, if it comes out to be less than 1, then it is a gain in speed. And even you can check the MA as well. What is load? 50. What is effort? 200. So find out the load upon effort, and you will find 50 divided by 200 will be 0.25. Okay, so you will find that your MA is also coming out to be less than 1, and that's why your machine is also a gain in speed. All of you, is it very clear? All of you getting it? Okay, if you are getting it, please write down yes. Okay, please type yes if you are getting it. Okay, so we concluded that when my velocity ratio is more than 1, my machine is acting as a force multiplier. But when my velocity ratio is less than 1, then my machine is working as a gain in speed. Now we will talk about the third parameter. Let's talk about the third parameter. Okay, now what I am going to do, I am going to take a load. This is my load which I have kept. So how much is my load? Look at the load. How much is the load? So load is 50 Newton. And how much the effort I am going to do? So the effort is also going to be 50 Newton only. Okay, so my load is 50 and my effort is also 50 Newton. Okay, now let me mark the initial position of load and effort. So this is my load. So this at 8, this is the initial position of my load. This is the initial position of the load at the base of the 50. Yeah, this is here I am marking it. Okay, this is the initial position, and I'm going to keep the effort at 8 again. So this is the initial position of the effort as well. So I mark the initial position. Now I will lift, I will place this 50 Newton load at 8 and see what happens. So you will find there is a displacement of load and the displacement of effort. Now here let's find out how much is the displacement of load. So it started from here. From this point I mark it till here. So what is this? This distance is my displacement of load. What is this distance? This distance is my displacement of load. This is the distance of displacement of load, which are labeled as displacement of load. Okay, let's see how much is the displacement of effort. So from here I started, okay, it started from here and it reaches to here. So what is this? This distance is this distance is my displacement of effort, which we call as displacement of effort. You will find we are having displacement of load and displacement of effort. Now, just by looking at this diagram, you can figure out that in this very case, you will find that the displacement of load is same as the displacement of effort. And what is velocity ratio? So velocity ratio is the ratio of displacement of effort to the displacement of load. So here you will find both the values are same. So your velocity ratio is coming out to be 1. And since your velocity ratio is coming out to be 1, what you will find? Is it a force multiplier? No. Why? Because how much is the load? The same is the effort required. So is it a force multiplier? No, it's not a force multiplier because your displacement of load and the displacement of effort is same. And even the value of your load and effort is same. So what is this machine? So it is used to change the direction of force only. So why we are using it? We are using it to change the direction of force only. See, what I want to do, I want this load which is on the left hand side to be lifted up. But what I am doing, I am applying the effort on the right hand side in a downward direction. To lift an object in an upward direction, I am applying the effort in a downward direction. Okay, so that's why what we are doing, we are simply changing the direction of force only. Okay, please write down. Now I hope your idea is very much clear. If you have copied, type yes. If you have copied, please type yes. Okay, very good. So now I will stop sharing this. Okay, I stop sharing this. And let's do that. Okay, so what we say? Velocity ratio is defined as the ratio of displacement of effort to the displacement of load. And what we conclude, when the velocity ratio is greater than 1, it is working as a force multiplier. I had explained you now in the with the help of the simulation that when your VR is coming greater than 1, it is a force multiplier. When your VR is less than 1, it is a gain in speed or a speed multiplier. And when your VR is coming out to be only 1, then it is change the direction of effort. So this is the use of velocity ratio. You will find velocity ratio and MA. They both are useful in determining the category of machine. With the help of the MA, we can categorize our machine, and the same with the help of the VR also, we can categorize machine. So if my MA is greater than 1, then it's a force multiplier. The same way, if my VR is also greater than 1, it is also a force multiplier. Then if VR is less than 1, it's a gain in speed. If MA is less than 1, it's a gain in speed. And if MA and VR both comes out to be 1, or if then it is change the direction of effort. Okay. What is the unit of velocity ratio? Remember, the unit of MA was, there was no unit to MA. The same way, there is no unit to velocity ratio as well. Why? Because it is again the ratio of two similar quantities. That is the displacement of effort and displacement of load. So since it's a ratio of two similar quantities, even they will not have any unit. Now we will talk about two more important terms. The first is work input. Okay, now what we call as work input. Now here, try to understand when I'm using the word work, I will actually talk about energy, because when the machine is doing some work, it requires energy. Okay. So what is work input? So it is nothing but it is the work done on the machine by the effort. You have to remember these terms. It is the work done on the machine by the effort. So what is work input? So it is nothing but it is the work done on the machine by the effort. So it is the work done on the machine and by the effort is called as work input. Obviously, see, there is a very simple condition applicable here that you have to do some work on the machine and the machine will do some work on the load. Okay, so that's why the work input, whatever the work we have to give to the machine, the work is done is equal to the work done on the machine by the effort. Effort is nothing but the force what we are applying. So what we apply is the effort, and that's why we call it a work input. Now, what is work output? So if you define work input, it is nothing but it is the work done by the effort. Okay. And what is work output? So work output is the work done by the machine. Now try to understand the difference here. It is the work done by the machine. Okay. But on load. Okay. So work output is nothing but it is the work done by the machine on the load is called as work output. And if you define it in simple statement, it is nothing but it is a work done on the load. See, I will again tell you very clearly that whenever we use machine in a system, okay, assume I want to lift a heavy object, but I cannot able to do it. So what I will do, I will not lift it directly, but in fact, what I will do, I will lift it with the help of a machine. So what I will do the work on the machine, and in turn, the machine will do the work on the load. Okay, so whatever the work done on the machine by me, by the force applied by me, is my work input. And whatever is the work done by the machine on that load to be lifted is work output. So work input is work done by the effort and work output is work done on the load. I hope you are very clear now what is work input and work output, class. Okay, please copy it. Now we will talk about another very important term, and that term is called as efficiency. So let's talk about what is efficiency. So efficiency of a machine is nothing but it is the ratio of work done on the load by the machine to the work done on the machine by the effort. Okay, so this is the ratio, but in simple terms we will define efficiency as work output upon work input. What is efficiency? The efficiency is nothing but it is the ratio of work output upon work input. Means how much is the work done by the, how much is the work done on the load to the work done by the effort. Okay, so what we can say that the efficiency of a machine is the ratio of work done on the load. Work done on the load is nothing but work output, and to the work done on the machine by the effort. So by the effort means what we are applying, that is work input. So in simple words, we will say that efficiency is the ratio of work output to the work input into 100. So into 100 means what? The efficiency is always calculated in percentage. Okay. So the efficiency of a machine comes out to be work output upon work input. In simple terms, if you want, I can further reframe this. You can also write down that it is actually efficiency. If you see that it is the useful, write down, useful work output divided by total work input. You can also define efficiency in this way because I'm using two terms here. One term is useful and the second is total. Now what is efficiency? Useful work output divided by total work input. Means how much is the total work we have done on the machine and how much is the useful work we are getting from the machine. So assume, just for the sake of your understanding, if I say that the total work input, the total work input is 100 joules. How much is the total work input? 100 joules. And the total, sorry, and the useful work output from the machine is 75 joules. Okay. So how much is the total work input? So the total work input is 100 joule, but the useful work output is coming out to be 75 joules. Okay. Means what? Means the total work input on the machine is 100, but the machine is converting out of that 100, only 75 joule is being converted for useful work. Okay. So in this case, you will find the answer will come out to be 75 divided by 100 into 100. And what you will get that the efficiency of the machine is coming out to be 75%. Now, what is the meaning of this word? The efficiency of the machine is 75%. It means that whatever the energy you give to the machine, whatever the energy you give to the machine, out of that only 75% is being used for the productive output. Only 75% is being used for the functioning of it. Okay. Then you will ask me, sir, what about that 25%? So the 25% is being utilized in doing some, or that 25% is a waste of energy. That 25% is a wastage of energy. Okay. Don't worry, I will further explain this efficiency again. Okay. So what will be the unit of efficiency? So again, efficiency also has no unit because it is a ratio of, again, work upon work, two similar quantities. But remember, we always calculate efficiency in percentage. So if you want to find out the efficiency in percentage, you multiply by 100. Otherwise, we can say that the efficiency is less than 1. So it's very important to know how efficient a machine is. Exactly. The machine which is more efficient means it is more productive because it is converting more of the given input, energy to the output. Okay. When energy is supplied to a machine, by applying an effort, it overcomes the load by doing some useful work on it. Okay, so what happens? So when the energy is supplied to a machine by applying a effort, it overcomes a load by doing some useful work on it. Exactly. I told you, because for using a machine, what we require, if I want the machine to work, I want to put the machine in operation, then I required energy. So when energy is supplied to the machine, obviously we are not going to supply the energy to something else. We are going to supply the energy to the machine. Okay. So when the energy is supplied to a machine by applying an effort, obviously, if you want to supply the energy, you are going to apply the effort. No one else is going to do it for you. So you are going to apply a effort. It overcomes the load by doing some useful work on it. So what the machine will do, it will overcome the load, and that whatever the work done by the machine on the load is my useful work output. So if you talk about an ideal machine, now there are two types of machine. One is ideal machine and the other is a actual machine. Now, what is the concept of ideal machine? An ideal machine is a machine in which you will always find that the output energy is same as the input energy. Exactly. What you will find in an ideal machine, your output energy will be exactly the same as the input energy. Means what? It means that assume I supply 200 joule of energy. How much energy or how much is the work done on the machine? 200 joule. So how much is the work done by the machine? Again 200 joule. Means how much is the total energy given? 200 joule. And how much is the total output energy useful output energy we are getting? The useful output energy we are getting is also 200 joule. So if we have this combination, then we call such machines as ideal machine. If I have a machine in which you will find that the input energy is equal to the output energy, then you can say that machine is an ideal machine. Okay. Now, what is ideal machine? So an ideal machine is the one, this is a very important statement, is the one in which there is no loss of energy in any manner. Exactly. That's the very important characteristics you will find of an ideal machine, that you will find there is no loss of energy in any manner in an ideal machine. So you will find that the output energy is always going to be equal to the input energy, and if you find out the efficiency of it, your output and input energy is same, so the output and the input work is also same, and you will find it, the efficiency will come out to be 100%. So that's the efficiency of a ideal machine. The efficiency of an ideal machine is 100%. But the interesting part of ideal machine is ideal machine do not exist in practical. Listen class, ideal machines do not exist in practical. Okay, if you want to find any ideal machine, you will never ever find it. Neither you can able to design an ideal machine. Okay, and I will talk about why you cannot design it, and then you will be very clear that yeah, it's something which is not possible. So what is actual machine? So it is a one which there will always be some loss of energy. What will happen here? There will be some loss of energy in its operation.
तर नाटक फारच अडकतो. तू आजचा दिवस ठेवशील आणि संध्याकाळी बघ काढून टाकशील तू.
You will find that in actual machine, there is some loss of energy during its operation. Okay, so whenever you are using an actual machine, there is some loss of energy when you are using it. And what is the reason for the loss of energy? So you will find the reason is that the moving parts are neither wetless nor frictionless. Obviously, try to understand class. This is a very fundamental reason why we cannot have an ideal machine. Why? Because if I want an ideal machine, you should have its moving part to be weightless and frictionless. And we know very well, if the object has to be weightless, it should have no mass. Is it possible to have something, to have a machine which is having no mass? Not possible. Whenever you design a machine, it will have some parts, and that parts will have some mass, and that's why it will not be weightless. So that's the reason why we cannot have a ideal machine. Why? Because if you want a machine to be an ideal machine, its moving part should be weightless and frictionless. But the problem is that it's not possible. That's why you will find that there is some loss of energy when we are using the actual machine. Why? Because the moving parts of the machine are neither weightless, not possible, nor frictionless. So we cannot attain 100% frictionless surface as well. So even that is a reason why we cannot have a ideal machine. The same way you may find that if there are different parts used in that machine, these parts are also not perfectly rigid. So they are not perfectly rigid. Even this is a reason why we cannot have a ideal machine. But hypothetically, you can consider an ideal machine, and an ideal machine is the one in which there is no loss of energy. Whereas in actual machine, there is some loss of energy, and that's the reason why you will find that your actual machine is not 100% efficient. Your actual machine will always be, it's the efficiency of your actual machine will always be less. Why? Because whatever the energy we have given to the machine, out of it, some of it will be utilized to overcome the weight, to overcome the friction, and due to the non-rigid parts of the machine. So that's why there will be some loss of energy and your efficiency will not be 100%. So we don't have any machine having efficiency as 100%, because ideal machines in practical ideal machines do not exist. So now let's talk about another very important relation, the relationship between efficiency, MA and VR. Let's look at this very interesting relationship is there between efficiency, MA and VR. We know what is efficiency, we know what is MA, we know what is VR, we know what is work input and work output, and we know what is load and effort. Since now we are very much familiar with the terms of machines, so let's talk about what is the relation between MA, VR and efficiency. You know very well, efficiency is what? Work output upon work input, or you can say useful work output divided by total work input. So what is work output? Now let's understand work. Let me recollect the concept of work, what we have studied in chapter number 2. So work output. So work, you know very well what is work. Work is force into displacement. Yes or no? Force into displacement. So here I will say work output. Okay, remember there is a relation. How we define work beta? So we know very well. We say work is equal to Fs, force into displacement, into cos theta as well. But if the force and the displacement are in the same direction, then the theta will be 0 and cos 0 is 1. So it is same as force into displacement. So here the same way I am talking about work output. So work output will be what? So it will be force into displacement. So it will be load into the displacement of load. Yes or no? So the force is the load here, and what is getting displaced? The load itself is getting displaced. So what is my work output? With the reference to the work formula, it will be force into displacement, and here the force in the output is the load into the displacement of. Then the same way, what is your work input? So work input is something what we are doing. So it is again force into displacement, but we are applying the force, and I told you the force what we apply is called as effort. So work input will be effort into the displacement of effort, because the work formula is force into displacement. So work output is force into displacement of load, and work input is equal to effort into the displacement of effort. Okay, so if I rearrange it, so my efficiency is equal to work output upon work input. But for work output, I am writing load into displacement of load. For work output, what I am writing? Load into displacement of load divided by work input. For work input, it is effort into displacement of effort. So it is effort into displacement of effort, which is equal to, now what I have done, I have just taken these two terms together. This, so what is this? This is load upon effort into displacement of load upon displacement of effort. But there is no term such as displacement of load and displacement of effort, but we have the reverse of it. So what I have done, I have taken this, I kept this term as it is, into I have taken the reciprocal of this. So if I have taken the reciprocal of this, it will be 1 upon displacement of effort upon displacement of load. So we have taken the reciprocal of it. And what is load upon effort? So you know very well that load upon effort is nothing but it's my MA. And what is the displacement of effort upon displacement of load? So the displacement of effort upon displacement of load is my VR. So what we get from efficiency, So efficiency is equal to MA upon VR. Why? Because MA is load upon effort. So instead of this term, I have used MA into 1 upon, for this term, I use VR. So this is my VR and this is my MA. So I get efficiency is equal to MA upon VR. I have purposely taken the reciprocal of it and my efficiency is coming out to be MA upon VR, or we are having MA is equal to efficiency into VR. So this is the relation between efficiency, MA and VR. So you will find there are two formulas to calculate the efficiency. How many formulas do we have, class? So we have two formulas by which we can calculate the efficiency. The first is MA efficiency is equal to MA upon VR, and the second is efficiency is equal to work output upon work input. So these are our two formulas by which we can easily calculate the efficiency. So efficiency is equal to MA upon VR. Now try to understand this. This is a very interesting concept. Okay, that in actual, whenever you are going to use a actual machine, you will find that the MA of all the machines is always going to be less than its VR. Okay, so this is what you have to understand as long as efficiency is concerned, that efficiency is the ratio of MAs to VR, and in actual, means for all the actual machines, you will find that your MA is always going to be less than the VR of that machine. Let me explain you a bit of it with the help of this table. So assume, we are just assuming these facts, okay, for the betterment of understanding the topic. Assume I am having an ideal machine. So in ideal machine, what you will find, your MA is coming out to be 4, assume. So your VR will also come out to be 4. So your MA is 4, your VR is 4. So efficiency is equal to MA upon VR into 100. So 4 into 4 is 1, into 100 is 100%. So what is the efficiency of an ideal machine? 100%. But in actual machine, our efficiency, as I told you, the efficiency will never be 100. It will always be less than 100. So what is the cause of that? Is it due to MA or is it due to VR? So you will find, if I take the same machine as an actual, then the VR of ideal machine was 4 and the VR of actual machine will also be 4. So remember, the VR parameter of ideal machine and actual machine will remain the same. Whether it is an ideal machine or whether it's an actual machine, the VR will always remain the same. But what about the ideal MA of an ideal machine? It was 4. But what is the MA of the actual machine? So the MA of the actual machine will be lesser than the MA of the ideal machine. So there is less MA. So MA will be, assume it is 3. So now if you calculate MA upon VR, 3 into 3 divided by 4, which is 0.75, or if you multiply that value by 100, we get the efficiency to be 75%. So understand that when it comes to the actual machine and the ideal machine, you will find the VR of ideal and actual machine remains the same. The velocity ratio of ideal machine and actual machine remains the same. Then what changes? So you will find that the MA of our actual machine will be lesser than the ideal machine, or in comparison to MA and VR, you will find that MA is always going to be less than that of VR. And that's the reason why our machines are not 100% efficient. It is not due to VR, it is due to MA. Oh, okay. So now I stop it first of all.